Hello, everybody, and welcome to this month's Astronomy on Tap, Santa Cruz. We're so excited to have you all here tonight and so excited for our speakers this evening. I'm Alex. I'm a grad student at UCSC, and I will be your MC host for the evening. So we've got two wonderful speakers for you tonight, and we're focusing this evening on fast radio bursts. And this is a topic that is near and dear to my heart, as it's also the what I study and the research that I do. So our speakers this evening are Sunil Simha of UCSC and also Jay Chittidi of UC Boulder. So excited to have you all with us this evening. I hope you've got something to sip on, alcoholic or non. I've got I was going to say little margarita, but it's not so little. I have to grab it with two hands. So that's what I'm having this evening. Hope you all have got something to keep you company that you can nurse over the next, hour of these talks. Also, one of our speakers, Jay, came up with, I think, correct me if I'm wrong, when he comes on, we'll talk about it a little bit more. But we have a special drink for the evening called a Fast Radio Burst. And it's pretty much a shot of whatever you like, followed by a chaser of a cosmic cranberry kombucha. So we'll see how that tastes. Personally, it sounds a little bit strange to me, but I'm excited to give it a go. All right, so also there will be a quiz during the sort of intermission between Sunil and Jay's talks. I'll go over the questions with everyone, and then there's a link to a Google form that will be shared on the YouTube comment section down there that you can find and fill out. And then we'll go over the answers at the end, and there might be some prizes in the future of this. We're still trying to figure out how to work that out so we can, reward the awesome work and knowledge of our viewers. So yeah, let's go ahead and get started. So I'm going to bring on Sunil.
Hey, Alex.
Hello, welcome.
Thanks, Alex. Nice to be here.
Can you hear me all right?
Yep.
Okay. Yeah, thanks for joining us. I see you pretty much every week, but it's good to see you in this context. Excited to hear more about and see you share with the public everything you've been working on. So I'll leave you to it.
Okay. Let me just share my screen. Okay, can everyone see my presentation? Oh, okay, well, I'm assuming you can. So thanks, Alex, for having me here, and thanks to all of the team of Astronomy on Tap. So my name is Sunil Simha. I am a graduate student at Astronomy, the Department of Astronomy at UC Santa Cruz, and I am working on the topic of fast radio bursts. I'm currently doing research on that topic, and this is in collaboration with the F to the 4th team, Fast and Fortunate for FRB follow-up, as well as the Craft team. And I'll be briefly talking about what fast radio bursts are. They have been an enigma for more than a decade now. And I'll be briefly talking about how they were discovered, followed by how we are able to pinpoint their location in the sky very precisely. And finally, I will talk about a few theories we have as to how they're being produced or what exactly is producing them, with some observational information that we have regarding this. So let's get started. Right, so if you've been paying attention to any of the science news, sorry. Yeah, any of the science news recently, you would have seen articles like this talking about astronomers detecting really mysterious bursts coming from places in the universe far out, closest fast radio burst found. Could these be aliens? So there are a lot of articles of asking if there are aliens, because these are mysterious signals that seems to be coming from outer space. All of this stuff is very exciting. So are these aliens? We don't think so, but there's always hope, that it could be an alien. So fingers crossed, at some point we may actually have an alien signal coming towards us. But for now, what do we know about fast radio bursts? What are they? So fast radio bursts, as the name suggests, are millisecond duration radio transient events. So that's a fancy way of saying these are basically Christmas lights out in space, but they're coming in radio waves, not visible light. Some of these fast radio bursts are known to repeat, but most of them don't. By repeat, I mean that we see bursts coming from the same place and with the same burst properties after a bit of time. Sometimes a few days, sometimes a few hours. It's sort of unpredictable. But some of these repeaters are periodic. We also know that these are extragalactic, and I will get to the part how we confirm this a bit later. But for now, let's just take it as a known fact. These are also extremely bright if they're extragalactic, because if these flashes can be detected from Earth and they're coming from all the way out in some other distant galaxy, they must be bright, otherwise you can't see them. We currently don't know any sort of optical counterpart. By that, I mean we don't observe any flash of visible light followed by the radio emission. So we don't think that this class of events has any optical light associated with it. And they seem to occur rather frequently. So every day, roughly 4,000 of them occur. So if you were to be able to have radio eyes and you could spot them, this is basically what the sky would look like, this video. So how exactly were they discovered? Their discovery is a rather fun story, actually. And so David Narkovic, an undergraduate student at West Virginia University, who was working with Duncan Larmor, discovered them in 2007. And he wasn't really looking for them. He was going through some archive data from the Parkes Radio Telescope in Australia. And if you look at the paper that they published, you would notice that this particular FRB event was actually detected back in 2001. So how did such events fly under the radar for so long? So to understand that, we need to first understand what David was looking for. So David was going through Pulsar archive data. So what are pulsars? Pulsars are extremely compact objects called neutron stars. So neutron stars are what you get after a massive star, star that is more than a few times massive than the sun, goes kaboom in a supernova, and it leaves behind its extremely compact core. This core has the mass of a few times that of the sun, so sometimes like 2 or 3 times solar masses, and it spans a few miles across. So you can think of it, if you think about it, you can place one of these objects right on top of Manhattan Island, and it would just fit. So extremely dense objects, naturally, And they're also very fast rotating. So some of these pulsars rotate once every second. Some rotate even 1,000 times faster. So extreme objects in general. So pulsars are interesting because they have light coming out from their magnetic poles. And their axis of rotation is sort of misaligned with these magnetic poles. And that is why they kind of behave like lighthouses or sirens. So whenever this pulse of light, this beam of light passes by us, we observe it as a pulse. So these are extremely periodic, very stable rotators, and we have discovered numerous pulsars. So light coming from pulsars has this specific property that we can use to understand the space, the material medium that it's traveling through. So you might have heard about the process, the phenomenon called dispersion. So basically, when white light passes through a prism, it gets dispersed into its individual components of light. And this is because the individual components have different speeds in this material medium. The same thing happens to radio waves traveling through plasma in outer space. Space is not really empty, so it has a bunch of gas, it has mostly plasma, so electrons, protons, charged particles of other kind. And when radio light passes through it, it gets dispersed, which means higher frequency radio waves travel faster than lower frequency radio waves. And when it reaches Earth, if you plot the time of arrival of these pulses against time, against the frequency, you get this characteristic shape, as you can see here in the plot towards on the right. So the black line that goes from left to right is essentially all these pulses arriving at different times, the pulses of different frequencies. So you would have multiple streaks like this if you were to get all of these repeating pulses that you get. FRBs look exactly like pulsars, but with one key difference. Most FRBs just have one single pulse, and what FRBs have a much larger dispersion than regular pulsars. By dispersion, I mean the time difference between the lowest and the highest frequency, the arrival time difference, basically. So FRBs seem to have a much larger dispersion, so sometimes lasting a few seconds almost. And this is one such FRB, the first FRB that was discovered. So as you can see over here, the pulse, the time of arrival delay was of the order of a few seconds, so half a second in this case. So why does this dispersion happen? Like I said, it's because of the plasma that the light is traveling through. And the more plasma you have between us and the source, the more dispersion you have. And that is why when this FRB event was first discovered, we thought that it was coming from outside our galaxy because there was no way that our galaxy contained so much plasma in that direction. So that's why we know, we suspected that they were extragalactic and they were extremely bright, but we need to verify this assumption. So how do you do that? The easiest possible way, the most intuitive way to do it is through by capturing a picture of it. So you just point your radio telescope at it, and if you were to spot this FRB coming from a different galaxy, it would show up on top of a galaxy. So that's the principle, basically. Although there's one catch, there's a problem. So if you think about radio telescopes as cameras, they have a problem with the resolution. So all of you would have cameras on your phones, and you have a certain megapixel count on your phone, right? The higher it is, the better resolution your pictures have. So radio telescopes have a fundamental pixel size that is determined by the physics of diffraction of light. And that limit is given by this ratio, the wavelength of light, lambda, divided by the diameter of the telescope, d. So lambda by d gives you the angular size of your pixel, basically. And if you want to get an idea of how big these pixels are, here is a picture showing the lambda by d circle superimposed on top of a picture of the moon. So each of these single circles represents one such pixel when observing with the Arecibo telescope. So as you can see, we don't really have a good angular resolution when observing with a single dish radio telescope. So what is the solution here? So if you look at the formula, and if we want to locate FRBs rather accurately, we need a megapixel count that is about 1,000 times higher. So what can we do? So if you look at the formula, the answer presents to you naturally. You basically need to increase the diameter of the telescope, or increase d. Now, this is hard because we don't really have the kind of structural materials that can hold up, a telescope that are kilometers or even miles across. So scientists have come up with a clever technique to essentially synthesize a large radio dish without actually building one. The way they do that is by having an array of antennae spread across a few miles. So this picture over here shows the VLA, the Very Large Array, in Socorro, New Mexico. And it's basically a bunch of radio dishes located in a Y-shaped array. And by adding the signals received by each of these telescopes in phase, one can essentially synthesize a dish that is right about as big as this entire array. So by doing this, you can improve your angular resolution and therefore do amazing things. For instance, take a look at this image of the black hole that was recently published by the EHD collaboration. This image was produced by adding signals from dishes that were spread apart by a few continents, actually. So scientists were able to get a very exquisite angular resolution and were able to produce this image. So this is a really powerful technique, and these can be applied to FRBs as well. So here are a bunch of galaxies with the FRB location in the white circles or white ellipses. So these have been localized using the ASCAP telescope, the Australian Square Kilometre Array Pathfinder. It is also an interferometer, just like the VLA. And using that, we are able to locate the FRB very precisely. And we are able to show that these are actually coming from other galaxies. So we know for certain that these are extragalactic signals. So we now know that most FRBs are extragalactic, but we don't really know how they're being produced. But we recently got an observation, by we, I mean the Chime collaboration, recently had an observation in April of an FRB-like event that was coming from a galactic source. So this is the first time we have observed such an event. And this was coming from an extreme object called a magnetar. A magnetar is basically a pulsar, but with a magnetic field that is several times stronger, several tens of, thousands of times stronger than a regular pulsar. So clearly that is one candidate that can produce an FRB-like event. Other theories that could produce FRB events could be neutron star mergers or some sort of extreme black hole activity. But so far, we haven't really observed any other activity apart from magnetar bursts. This magnetar is called SGR 1935 plus 2154. It's not a really fun name, but hey, it's producing some fun physics. So we're able to observe that. There's still a long way to go. We don't really know if all FRBs are produced the same way, especially the repeating FRBs. We don't really know how they're being produced or why some of them are even periodic, with periods lasting a few days to a few weeks. But that's a work in progress. And hopefully within the next decade or so, we will be able to find out what FRBs are, how they're being produced. However, for now, we can still do a fair amount of cool science with FRBs, which my friend Jay will talk about soon. But I am ready to summarize my talk at this point. So if there's anything I'd like you to take away from this talk, it is that FRBs are very energetic and mostly extragalactic radio transient events. They also have large dispersion measures, which means that the light from them is passing through a ton of plasma, which means that they're probably extragalactic, well, definitely extragalactic. They were discovered in 2007, and we have been successfully able to pinpoint their location using radio interferometry. And we have recently discovered galactic magnetar activity that closely resembles FRBs. So yeah, stay tuned in the future for further development in this rather exciting field of FRBs. And at this point, I've come to the end of my talk, and I'd be happy to take any questions. Thanks for listening.
I'll give you a round of applause. Really nice talk. Thank you, Sunil. So, are you ready to take some questions from the audience?
Sure.
All right. So one first question, well, first starting with a comment, great talk. What would convince you, what would convince you that it was an alien signal? And then I do have a follow-up to that.
That's a good question. So if something is an alien signal, you would have to have some sort of encoded information. So if you just have a single burst, that doesn't give you a lot of information. But if you receive something that looks like Morse code, for instance, that's saying something. If you were to receive a byte stream, for instance, like, you got a bunch of zeros and ones, like you have a bunch of beep, 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 that sort of stuff. That's an alien signal for sure.
Okay.
So, yeah.
Nice. All right. And then another question, did you mention the range of radio frequencies that these cover? And if it's in the gigahertz ranges, has anyone considered using the ATA at Hat Creek to image these or to search for them?
I'm not sure if people have imaged them using the ATA, but yeah, if it's an interferometer and it can be discovered. So there are some challenges to using interferometers even. So interferometers have a very small field of view, and so you would have to do some sort of fancy, how do you say, interferometry. So basically you want to first observe in a non-interferometric mode, and then when you detect the FRB, you want to switch to interferometry or do it at a later time. So if ATA has that technology, it can be done.
Cool. Okay. And follow up to the alien signal question, how did the aliens learn Morse code?
I don't know. That's just a speculation of mine. I mean, if we were to send signals of our own, right? I think we have done it in the past.
Yeah.
Yeah, I forget the project in particular, but when testing out the Arecibo, I think they tried transmitting radio waves as opposed to receiving them. And I don't think we have gotten a reply back yet.
They're still decoding the Morse code to try to figure out what to send back. Okay, another question just came in. how much is the fact that FRBs don't emit outside the radio range an indicator of what could be causing them?
That's a good question, and I don't really have an answer to it. But well, it certainly constrains models of emission. For instance, we know that the SGR event that I talked about, the galactic magnetar event, that does have a counterpart, but in X-rays. So whatever model explains this emission must explain the X-ray emission also. So you can't have any sort of emission model. So that's the thing, right? But at this point, there are so many theories that it's really hard to say, and we just have one observation of it. So yeah.
Nice. Wow, you got some really good questions. And then the final question that I have to ask you is the theory of light sails. And of course, this goes back to aliens once again. But how do we know that the FRBs are not, aliens using light sails?
Well, we just think that it's not, but then again, if it were, I mean, to use a light sail, I don't think you would have radio waves, would you? I would expect you would have like some sort of optical or UV emission, a bit more energetic. So yeah,
well, there you go.
I don't know.
There's the answer for the people. Hopefully they accept it. We'll see.
Yep.
Okay, I think that's all of the questions that we've got for you this time around. So thank you again for that wonderful talk.
Thanks for having me.
Yeah.
Wonderful to be here.
Well, hopefully you stick around and we'll see you again at the end.
Sure.
To have our celebratory drink.
Bye for now.
Okay, bye for now. Thanks, Sunil. All right, and I was told to once again show off this beautiful margarita. This is compliments of the house bartender, aka my cousin. Even put a nice little straw in there for me. And then the drink of this evening is the fast radio burst. And so that is a shot of a drink of your choosing. Could be water, that's fine too. I think I've got bourbon here. And then a chaser of just some cosmic cranberry kombucha. So we'll see how that goes. But I think, bourbon and cranberry usually go well together. All right, so now let's move on to the quiz. And you all can follow the link to the Google form that should be listed on the YouTube and follow along with me as I ask you all the questions. And let's get started. November trivia. Welcome to November. This year is flying by. So this, the theme for this month's trivia is seasonal astronomy. All right, I hope you're ready. Question number 1. There will be a bright meteor shower visible mid-November. What is the name of this dazzling display? A, the Leonids, B, Geminids, C, Perseids, or D, Orionids? There will be a bright meteor shower visible mid-November. What is the name of this dazzling display? All right, moving on to the next one. Question 2. The moon will look slightly darker for a penumbral, on November 30th. The moon will look slightly darker for a penumbral on November 30th. And it's giving you a nice little clue right here. All right, and on topic. So on our FRBs, The most recent discovered fast radio burst was accompanied by emission in which other wavelength? A, optical, B, infrared, C, X-ray, or D, microwave? The most recent discovered fast radio burst was accompanied by emission in which other wavelength? A, optical, B, infrared, C, X-ray, or D, microwave? Okay, next question. What year were FRBs first discovered? 2007, 2020, 1920, or 3005? Hopefully we're not you might be giving out some free points right now. And then I'll circle back to the first questions as we go, once I finish going through these. And 5, what is the term used for young neutron stars, the engines that drive FRBs, what we think to drive FRBs? A, magnetos, I think that's the right one. B, reptars, that sounds pretty plausible too. C, YNSs, or D, magnetars? A, magnetos, B, reptars, C, YNSs, or D, magnetars? Okay, a nice true or false for you. True or false? All FRBs are repeating and periodic. That's a tough one, I have to say, because I feel like there are a lot of qualifications that you could make depending on how you want to answer that question. But true or false? All FRBs are repeating and periodic. All right, and number 7. In 2015, peritons were found to be the result of the premature opening of microwave oven doors at the Parkes Observatory. I love this story, it's so funny. Peritons are named after a mythical creature made up by which famed author? A, J.R.R. Tolkien, B, Jorge Luis Borges, C, Virginia Woolf, or D, Maya Angelou? I was just telling my dad this story the other day. Thought it was so funny. In 2015, peritons were found to be the result of premature opening of microwave oven doors at the Parkes Observatory. Peritons are named after a mythical creature made up by which famed author? A, J.R.R. Tolkien, B, Jorge Luis Borges, C, Virginia Woolf, or D, Maya Angelou? That's a tough one too. All right, and we'll hold the answers to the end. So let's make our way back. So back to seasonal astronomy. Question number 1, there will be a bright meteor shower visible mid-November. What is the display? What is the name of this dazzling display? A, the Leonids, B, the Geminids, C, the Perseids, or D, the Orionids? And I hope you all are just furiously filling out your Google Forms, checking answers over and over, ready to win this imaginary prize that is really just my praise to you. I hope that's enough. And number 2, the moon will look slightly darker for a penumbral blank blank on November 30th. And this little animation is giving you a hint. Wink, wink. The moon will look slightly darker for a penumbral blank blank on November 30th. I hope we're good to go. And hopefully you all will all get 100%. All right. So now I hope you're ready for our next speaker. After you've exercised your brain a little bit with these questions, now we can let somebody else do all the heavy lifting. So I'll go ahead and bring on Jay and welcome him to the metaphorical stage, our virtual stage.
Hey, Alex, good to see you.
You too. How are you doing this evening?
I'm doing good. My cat probably will be jumping around the background. She was having a mood when Sunil was speaking, but we'll see how she likes my talk.
I think she'll love it, and I think the audience will love her. So no worries. So what will you be talking about this evening?
I'm going to be talking about, should I go ahead and start sharing my screen?
Sure, go ahead, yeah.
Sweet. Let me know if you can see that.
Beautiful.
Excellent. So Sunil just talked to us a little bit about what fast radio bursts are, how we've discovered them. And now I'm going to take a total different turn. I'm not going to care what fast radio bursts are. This is really the research that Alex, Sunil, and I do. But all I care about is how we can use fast radio bursts to solve a separate mystery about missing matter in our universe.
Nice.
Again, my name is Jay Chittidi. I go to CU Boulder, but last year I worked at the Mariah Mitchell Association in collaboration with UCSC to study this topic.
All right, I'll leave you to it.
Sweet, thank you. So I'm going to take a step back and I'm going to give you what I'm calling an astronomer's quick and dirty overview of cosmology. If there's any cosmologists in the audience, I sincerely apologize. You're probably going to hate this, but a natural question we can ask is, what exactly is our universe made of? To answer this, the ESA, the European Space Agency, launched something called Planck. Its mission was to measure the small, tiny variations in the temperature, or you can imagine just the temperature from light that happened 379,000 years after the Big Bang. So this is some of the earliest light in our universe, and it has an associated temperature. But because of the expansion of the universe, when that original light, it was really hot, it's actually cooled down now because of expansion of the universe. And it's really only about 3 degrees Kelvin for all intents and purposes. For us, that's basically absolute zero. It's very, very cold. And what it studied was this map of the universe, looking at this temperature of that, this primordial light called the cosmic microwave background. Now, these fluctuations, the darker red parts are slightly hotter than the blue parts, which are slightly cooler. Now, these variations in the modern day universe represent variations in density. So wherever you see the dark red parts, there's more stuff. There's more galaxies, more stars, more galaxy clusters, really, than the lighter blue regions. And I'm going to skip over textbooks and textbooks of cosmology and say that in addition to this and a lot of theory, we are able to deduce 3 simple ingredients that our universe is made of. One is called baryonic matter. That you can take that as a buzzword for tonight. That's matter like you and me, or computers, stars, galaxies. Anything we can see is baryonic matter. Everything we can't see is not like us. You might have heard of something called dark matter. That is decidedly not like us. It doesn't interact with light. We can't see dark matter. There's a third ingredient called dark energy. I have no time to explain dark energy. I don't even think I know what dark energy is. So please do not ask me any questions about dark energy. So what does that picture look like of those 3 ingredients? You only need 5% of the universe to be stuff like us, baryonic matter, baryons, to complete the universe. About 25% is dark matter. And 70%, the overwhelming majority of content in our universe, energy, mass energy content, we call it, is dark energy. Again, do not ask me about that. We can estimate the fraction of baryons in our universe is 5% by adding up all the light we see from galaxies because stars and most of the material that we would see would be sitting in galaxies. And it turns out we only see half the light when we estimate a mass from the amount of light we see. We only see half the baryons in that emission in light compared to that 5% that we were expecting. So we saw like about 2.5% of our universe in light. This other 2.5% of baryonic matter is hidden or missing. Missing if you want to sound cool, hidden if you're being a little bit more precise about what's going on. So where is that missing matter? We think it's in something called the cosmic web that's connecting galaxies and gas between them. On the right here, I have an image of a poster that NASA released just a week and a half ago in honor of Halloween. It shows I'm sorry if you have arachnophobia, by the way, what must be a 3 million light year size spider sitting in our universe. It says the cosmic web presents dark matter. Again, dark energy and dark matter are not really the focus of this talk, but you can ask me maybe a little bit of questions about dark matter. I might ask Sunil to help out later. But in any case, it turns out that this missing matter is really, really, really hot. And it's also super low dense. What happens is galaxies expel all this extra matter that's again hard to see. And it's sitting in the halos where dark matter dominates around galaxies. And then just take it one scale bigger, those galaxies are connected by even more diffuse and also hot gas that we can't see in emission. So that's what we call the cosmic web. We can't really see the cosmic web, but we can infer its existence both from theory and a couple observations. And I'm going to tell you how this plays a role in what we think or how we know the missing matter is there. So cosmology predicts there's going to be more of this baryonic matter, that's matter like us, than we actually see. And we think that it's in the cosmic web of hot gas between galaxies. So you might be wondering, Jay, what the heck does any of this have to do, with FRBs? It's not a talk about cosmology, so we talk about FRBs. It actually plays a really important role. I'm going to take us back to what Sunil helped explain, this effect we call dispersion. There's going to be more dispersion as long as the radio emission from the FRB travels through any baryonic matter. It doesn't care how diffuse it is. It doesn't care how dense it is. If there is baryonic matter, if there is hot diffuse gas, if there's a cosmic web, the signal from a fast radio burst happening in a faraway galaxy is going to be more dispersed because of the cosmic web. So I have a little plot here, a little sort of schematic on the left, where it's showing two galaxies. I know they look the same, but imagine the left one's further, or excuse me, the left one's closer and the right one's further away. Because of dispersion, if there is invisible hot gas, we're going to measure a smaller dispersion measure than if the galaxy was much further away. And that's because as we look further and further into the universe, we're going through more and more of the cosmic web. So more of it's going to contribute to the dispersion measure. We're going to have a larger dispersion. There's actually a lot of challenges to this. You might actually ask, hey Jay, that FRB went off in a galaxy. There's baryonic matter that we can see in that galaxy. How much dispersion is being caused by the host galaxy? It's actually not easy to measure that. I can tell you a little bit more about that later. We have a few ways to estimate it. But in any case, FRBs are offering us a way of detecting that missing matter. We might not be able to see it, but dispersion will tell us a lot about it. All right, I put a plot here on the right. Don't be afraid, I'm gonna walk you through it. What's shown here on the x-axis, so that's the horizontal axis, is something called redshift, Z, in astronomy. For our intents and purposes, just think of that as distance in the universe, where we're closest to us on the left and very, very, very far into the universe on the right. And on the y-axis, it says dm cosmic, that's the dispersion measure that's caused by the cosmic web. On the left, I have a little quick equation, should be easy enough. The dispersion measure from the cosmic web is just all the dispersion signal we measured at the telescope. We make an estimate for, hey, how much our Milky Way caused in terms of dispersion, because again, this signal is coming from outside the galaxy, has to travel through our own galaxy also to get here. And then we make an estimate and subtract off how much dispersion we think the host galaxy of the fast radio burst is causing. You do that quick equation, again, I'm skipping through a lot of details naturally, you get an estimate of the dispersion measure caused by the cosmic web. In effect, you've detected how much baryonic matter is between you and that galaxy. And that's what's shown on the y-axis. You can think of that as a number of baryons. The black line in this plot is showing from Planck. Remember, Planck estimated a bunch of wonderful cosmological parameters. It told us we expect 5% of our universe to be baryons. We make a bunch of inferences and say, as we go further and further and further out into the universe, we're going to be seeing more and more dispersion measure caused by the cosmic web. So that's what that black line is, the expectation we have for fast radio bursts to fall into. And then all these 8 plots are fast radio bursts that were detected by the group of researchers leading this paper, including JP Macquart. And what they do is they plot the estimate of the dispersion measure for the cosmic web for that specific fast radio burst as a function of distance. And as you can see, all those plots, there's about as much dispersion in the cosmic web. There's about as many baryons as we had expected from Planck. That's what that gray shaded area is showing. So in effect, the researchers of this paper that was published in Nature in June, some of our own collaborators here were working on that paper. They have in effect detected that missing matter. Even though we can't see it, dispersion allows us to measure it. And so we know it's there. This is sort of like a solution to this hidden missing matter problem. I'll just make a quick comment. What was very tragic was JP Macquart, the author who led this paper, a very prolific astronomer in Australia. He passed away only about a week and a half after, I think about a week or two after this paper was published again in Nature, which is very prestigious. So it was very sudden loss, and I think we're all still a little bit sad about that. But what was nice in the summer, about a month afterwards, there was an annual fast radio burst sort of convention, a meeting of astronomers who work in this field, and I think we all agreed that naming this relation, this distance versus dispersion measure of the cosmic web, it would be appropriate to name it the Macquart Relation, and so that's what we call it today. So this result was really hotly covered in the press. Futurity, Science picked it up, phys.org, Conversation, and really cool was CNN even picked it up. This was sort of a big news in the astronomy field, in cosmology and the like. And so in the end, it turns out results from FRBs agree with predictions for the missing matter. We know that that's generally in the cosmic web. Now you might ask, you know that it's there, what does it look like? Can we create a map of it? Wouldn't that be just the coolest thing? And I'm happy to say the answer is yes, with a lot of analysis. This is actually what Sunil and I worked on for the past year, and Alex as well, in a paper that my paper is in revision, Sunil's paper is published, I'll talk about that in a second. But we looked at one fast radio burst host galaxy. It's this beautiful spiral that we took an image of with Hubble Space Telescope, you might have heard of. There's Hubble, in the ultraviolet. So this is light we can't see with our own eyes, but our detector on the Hubble Space Telescope can see ultraviolet light. And what we did was we used, separate from this, visible light we can see, we split it up into its component colors. You can think of red, green, and blue. And we studied all those different colors in more detail. We call that a spectra. From that, this is how we estimated. We looked at the specific region around the fast radio burst, and looking at all this light, we were able to learn about star formation rate, and the amount of light that we get from that region. Combining some of those, we can estimate the dispersion measure caused by the host galaxy. Turned out to be it was really rough, I think around half to a fourth of the total dispersion measure picked up by the telescope was likely caused by the galaxy. That gave us a way to feed Sunil an estimate for the cosmic web contribution to the dispersion measure for his research. This was done by Sunil and again, Joe Burchett, who's now a professor, who was at UCSC, I believe, as a postdoc, and is now a professor at New Mexico State University. They took that estimate that we made for the contribution from the cosmic web along our line of sight, and by a technique developed by Joe, Sunil was able to work with him to sort of grow the cosmic web like something called Physarum mold. And I'm sure Sunil will be more than happy to answer more questions about that. But in effect, what Sunil did was looked at known galaxies between us and this galaxy that we're looking at in particular. We have surveys that tell us all about millions and hundreds of millions of galaxies nearby. Using the data, they basically gave the cosmic web food, because the cosmic web grows as it follows gravity. So things that are big, like galaxies, are naturally going to pull that cosmic web towards them. And that's sort of the inspiration for the model. They basically grew this cosmic web, and you can see this beautiful detailed structure from their simulation. This is really the closest I think we've ever gotten to mapping the cosmic web. And in fact, this is now a foundation for doing that using fast radio bursts. So we're building the framework that will allow us to very soon already infer maps of this cosmic web. Just give you a quick summary of my talk. Cosmology predicted more baryonic matter than we see. This effect, this dispersion measure effect from fast radio bursts, is what is allowing us to detect that hidden matter. And as we detect more fast radio bursts, we're going to be able to start mapping the cosmic web. And real quick, I'm sure I'm over time already, but these are just some of our F4 members. We're all over the world, from the Maria Mitchell Association on Nantucket Island to Santa Cruz, to Chile, Iceland, Northwestern, Cape Town, Hunter College. There are a few members that are not pictured, but we're really a global effort that are connecting with many more efforts in this field. And it's a very exciting time, I think, to be in the field of fast radio bursts and even the cosmic web. And so with that, I just want to thank everyone, my advisor at Maria Mitchell and Sunil and X, and everyone involved. Happy to take questions at this time.
Very nice. Yes, thank you, Jay. That was a really wonderful talk. Very, very well put. Nicely done. So are you ready to take some questions from the audience? They're lining up. Okay. So first we've got, how does one know that dark matter is hot, and what does that mean? How do we know the temperature of dark matter?
That's a great question. When I may have misspoken when I was talking earlier, this baryonic matter, this gas, that's the thing that I was referring to, that it's hot, and it's also sitting in the halos of galaxies. It's just very diffuse, we can't see it. What's dominating in terms of mass in galactic halos is dark matter. So there's just so much more dark matter. There's also this baryonic matter that's sitting there that is contributing to that 5% of all the mass that's in matter like us in the universe. Separately from that, I remember reading a few papers about dark matter before, and some people do refer to a temperature of dark matter. I suspect that has more to do with the energy of whatever particle is causing dark matter. So maybe energy is connects to us more in our daily lives than temperature. If there's anyone who studies dark matter in the audience, so that's not true, please jump in and correct me. But if you see somewhere that says dark matter temperature, they might be referring to the energy of whatever dark matter is. Yeah,
and I think like the leading, I guess, theory is cold dark matter, and that's because cold dark matter is better able to like coalesce and form the dense structures that we see throughout the universe and things like that. So, yeah. All right.
Maybe I'll just say one more thing about dark matter.
Yeah.
Because 25% of our universe, so about 25% of our universe is dark matter, only 5% is baryonic matter like us. Mm-hmm. Mapping the cosmic web is in a way mapping the dark matter. Mm. That picture of the spider where you saw the web, really if we could see dark matter, we'd see that most of it would be dark matter in that web structure. Very little of it is baryonic matter. So if we can map what we say is that the baryons trace the dark matter in the cosmic web. So in a way, you can map dark matter in our universe if you can map the baryons.
Wow, that's really, really exciting stuff. Okay, one more question. Does baryonic matter include the entire standard model?
That is a really good question. I would assume that the Planck 15 cosmology, the parameters that went into determining that 5% number, I would assume that that they employ only standard model particles, but that is beyond my realm of that's not necessarily what I study. I don't have as much experience as other astronomers in particle physics yet, so I hesitate to say, but that would be my best guess.
Another fun question for you. Are black holes dark matter?
That is a very cool question. I want to say no, because what forms a black hole is a star, and a star is decidedly baryonic matter. It's made of electrons and all this stuff. So whatever created the black hole I think is baryonic matter. I don't think a black hole is made of matter. I think maybe it's the absence of matter, but I really don't know much about black holes either. So jump in if anyone is a GR expert.
Someone in the YouTube comments.
There's always someone.
Okay, and then maybe you can tell us a little bit more about the slime mold.
Yeah, I might invite Sunil on here. I can give it in maybe broad strokes, but Sunil and Joe had developed a model that's what I'd say is probabilistically grows or maps the cosmic web. Mm-hmm. So it takes information that we know. We know there are galaxies here, here, and here. Naturally, the cosmic web, in our understanding, would be connecting these galaxies. So if there's galaxies really close together, we expect that their hot gas that's interacting with them is also connected. So it's actually a really sensible way to model it after this organism, the Physarum mold. Knowing an estimate of DM cosmic from any particular fast radio burst, knowing the things that are in the foreground, you can imagine those are the sort of the inputs to this model, and that's and Sunil, if you want to jump back in and take over, this is totally your work, so feel free.
There he is.
Hey.
Hello. Yeah, that was a great talk to you. But yeah, the Physarum model, the slime mold model, it's a way of visualizing your dark matter distribution, just like you said. And the way it works is we know that galaxies are embedded in this dark matter structure, the cosmic web. And so we can think of it as food particles for a simulated slime mold organism. So if you've ever seen a slime mold in a petri dish, if you have a bunch of food particles floating around in the petri dish, it will create a network-like structure connecting these food particles. And so that's what Joe and Oscar, who actually developed the model, tried to simulate. So they simulated the particles of slime mold. And they said, okay, the galaxies are food particles, now create a network that connects them. And that's what this simulation produces. It produces a density map of slime mold particles based on the information about the galaxy spatial locations that we provide as input.
Nice. Wow, well, it appears we may have lost Jay for the moment, but just in time, because we were all out of questions and it's time for us to go on to the quiz answers. There you are, Jay.
Sorry, I think the internet had a moment.
No worries. There's actually one more question if you want to answer this. Are dark matter halos part of the web, or are they more separate?
I'd say they're part of the web.
Mm-hmm.
In fact, you can think of them as the backbone of the cosmic web. We expected the baryonic matter, the things that are causing dispersion, trace. They're only a small fraction of it, and because gravity is what's deciding where these molecules go, the dark matter just has so much more gravity because it's so much more there's so much more of it that the gas is just following along.
Nice. All right. Well, thank you again, Jay, for a really awesome talk.
Thank you.
And I'll see you back here in like 2 minutes after I go over the quiz questions. Okay, Are we ready for quiz answers? Let's see how you all did. I hope it's tens across the board. Here we go. Answer time. All right. There will be a bright meteor shower visible mid-November. What is the name of this dazzling display? And the answer was A. I absolutely would have gotten this wrong. I am a horrible astronomer. Well, I hope you all did better than me. I hope you put A. All right, number 2. The moon will look slightly darker for a penumbral lunar eclipse on November 30th. So our answer here was lunar eclipse. Yeah, check that off. I know you all got that right. Okay, number 3. The most recent discovered fast radio burst was accompanied by emission in which other wavelength? And the answer to that one is C, X-ray. Got some high energy emission coming from that. All right, I'm good to go. I'm imagining you all giving me thumbs up, saying you're ready. And number 4, what year were FRBs first discovered? And the answer to that one, A, 2007. Yep. All right. And number 5, what is the term used for young neutron stars, the engines that drive FRBs? Unfortunately, the answer is not B, reptars. It is D, magnetars. Yep. All right, next question. Hopefully I'm not moving too fast for anyone. I think y'all can keep up. 6, true or false? All FRBs are repeating and periodic. And the answer to that one was false. Only some are repeating and periodic. And there's a lot of research going into, you know, what any of this means. What is a repeating FRB? What's a non-repeating one? How are they different? What's going on? So this is really a field filled with lots of mystery in a way. All right, next question. In 2015, peritons were found to be the result of premature opening of microwave oven doors at the Parkes Observatory. Peritons are named after a mythical creature made up by which famed author? And the answer here was B. I guess that's a picture of them there. Yep, got it. Okay. And I think that was our last question. Anybody need any answers again? We'll go through them quickly just so you can have another look-see. Pat yourself on the back for the ones you got right. Pat yourself on the back for the ones you got wrong. You know, it's a learning experience. All right. 2007. Our Lorimer burst. Magnetars, false. And Mr. Jorge Luis Borges. All right. So let's stop sharing, and I'm going to bring back on our speakers to have a little celebratory toast, drink. We've got our fast radio burst prepared and ready to go. What was that, Jay?
I said it's been a while since I've done this.
Oh, yeah, same. I haven't taken a shot in probably like a year. All right, and you know, if you've got cranberry juice, that's welcome too. A little cranberry and ginger ale, actually. That might be nice. Anyway, all right, so thank the both of you for coming here and giving some awesome talks, giving us all a wonderful evening in the midst of a very, very, you know, stressful time with everything that's going on. So we really, really appreciate you all being here and sharing your big brains with us and all the knowledge that comes with them. So cheers to you.
Thank you, Alex. Thanks for hosting. Sunil.
Yeah.
Thanks for having us.
Okay, here I go.
All right.
Woo. Well, that's good. Well, maybe. I'm still undecided if that was actually good. Yeah. I don't know about the combination of the two, but I'll definitely keep sipping on my kombucha.
Me too.
All right. Wow. So it appears that we have a three-way tie for the quiz winners. We've got Heidi Simpson, Al, it looks like, and Ratliff. So congratulations to the three of you. Yes, you get a round of applause, and you get an appearance from Puri. All right. Well, thanks everyone for joining in this evening. We had a really great time, and I hope that you all would join us next month. We've got speakers talking to us about black holes, and that will be featuring, let me check once more. I should have had this pulled up and ready to go. Okay, tentative title, Lighting Up Black Holes. And we'll be featuring Brenna Mockler and Sierra Dodd, both UCSC grad students. So please come back and join us for that. We'd be more than happy to have you once again to close out the year with Astronomy on Tap. So thanks again for joining us this time around. Hopefully you've had a good time learning some science, drinking your drink, snacking on something, and we'll see you again next time. Thanks again, and congratulations to our quiz winners. Good job.